Today we have with us Dr. Vijay K. Shah. He is an assistant professor at Cybersecurity Engineering Department in the College of Engineering and Computing at George Mason University, Virginia, USA. So he holds an adjunct faculty position with Virginia Tech and is a faculty member of Commonwealth Cyber Initiative, commonly known as CCI, a Virginia state-wide initiative to foster 5G wireless, autonomous systems, data, and cybersecurity research. His experimental research basically focuses on prototyping a next generation wireless communication and networking, particularly in 5G and 6G cellular networks. Others are open radio access networks, ORAN, AIML, and spectrum sharing. Uh, his research is generously by the National Science Foundation, National Institute of Standards and Technology, and Commonwealth Cyber Initiative (CCI), which I introduced earlier. He serves on a technical program committee (TPC) of several international conferences such as MobiHawk ICNP, and is the organizing co-chair of the IEEE workshop on next generation radio access networks, which was co-located in IEEE uh, GlobeCon 2022. So he's basically, as Sadhal sir told, he's the 2013 batch pass out. So like he'll be continuing with his topic that's road beyond 5G architecture, applications, and trends. So let's start. Thank you, sir.
Thank you. Thank you for the introduction. Um, I'm the I'm an assistant professor at George Mason University. If you don't know, it's a U.S. based or Virginia based school, very close to DC, the capital of the country. I direct this NextG Wireless Lab, and I'm also a part of this wireless cyber center, which is a really interesting concept. It brings about 12 to 14 faculties from different departments like ECE, computer science, cybersecurity, and other relevant, digital focused departments together under one roof to collaborate and to do meaningful research. So that's the Wireless Cyber Center. So as you see, my talk is road beyond 5G. So the first question is, how many of you know 5G? What is 5G to you? Do you know the difference between, let's say, 5G and Wi-Fi? Right? As a computer scientist, I doubt that we have very good understanding of 5G. So what I will do, I'll give very little crash course on 5G, a little bit of history, and then because Dr. Nandi mentioned that you should keep the discussion that what is the ongoing research in your lab rather than going into the depth. So I'm going to give you a very broad, let's say very high level understanding of the different research areas within 5G or within NextG that's going on in my lab. Okay, so I'm not really getting into the details. If you have any questions or if you're interested in a particular topic, talk to me or just send me an email. I'll be more than happy to talk about it. Okay, so let's get started. Okay, brief intro I just added after seeing Satadal nice slide. I said, okay, I should also, let's say, give a little introduction. So I was also in the same batch as Satadal, Rohit, myself, and Sais. We were sort of the four musketeers in the old days. So I started, I was in this batch from 2009 to 2013. And after that, I joined this company called Belltower, which used to be an on-site company. I worked there for almost 2 years. And then I went to US for my PhD. I skipped masters because I already knew that I wanted to do a PhD and build a career in research. I always wanted to be a professor. Okay, so that's why I did not do masters at that point. And then after that, I went to Virginia Tech as a research assistant professor, which is in a way glorified postdoc. If you guys are familiar with the concept of postdoc, it's a postdoc but glorified because it's an assistant professor, so you do get a lot of benefits. You do get access to the students. You do get access to the opportunity of writing grants and other things. And then since 2021, which is about 1.5 years ago, I joined George Mason as a tenure track assistant professor. I like to put that nice outstanding PhD award because that's the only award I have ever received until now. I hope that's not the only award then by the time I retire. but I'm really proud of that. My background, like you see, it's on NextG Wireless Communication and Networks, with a focus on 5G and NextG. Spectrum sharing was my PhD thesis topic, so that's obviously something that I'm still doing. And then there are several other relevant projects within the big umbrella of 5G. Okay, so will be the agenda. I'll try to go through, like I said, try to make a case for road beyond 5G, right? Now 5G is already being deployed, right? So what is next, right? And why do we really need a next G, right? Now people are talking about 6G. In the conference yesterday and day before yesterday, like some of the colleagues were saying that now India doesn't want to do 5G, India wants to do 6G, right? So I was, so it's already being discussed now. So I'll try to make a case. So basically, I'll look at the applications, because applications actually drive these generations of communication networks. And then what are the different trains, right? And then architectures. And then I will talk about some of the ongoing research in my lab. Okay. So, Tesla, I like this quote here. The Tesla actually sort of envisioned that the world is going to be like a brain where each and everything will be connected to each other. And now you see after 100 years, right, this thing is actually becoming a reality, right? With Internet of Things, now people are talking about Internet of Everything, right? So that's actually what's happening. And wireless is playing a big role, right? Wireless networks, or let's say information and communication technology in general. Internet is a big part of it. But if you look at, let's say, the access network, there is mostly the wireless piece, right? You do not really connect to the internet directly. There is some technology, right? Whether it's Wi-Fi, Bluetooth, WiMAX, 5G, 4G, there's some wireless technology, that connects you to that ICT technology, right? So, so that's a very interesting part that Tesla provided almost 100 years ago, right? So 4G and 5G, I'm still taking a reference of 4G because that's the latest technology that we can compare with the 5G. So they started addressing some of the challenges, right? But we're still not there yet. The vision of everything being connected to each other is not there yet. And the expectation is that the 6G possibly or 7G, we'll see that, will hopefully bring that to a reality. So now the question is just at a very high level, right? That where do we start? Where did we start? We started with 1G, right? There's obviously a first version of everything, irrespective of what software or what technology or whatever you do in life, right? So we started with 1G back in 1980s with just the voice, right? As long as you could talk to each other, that was the thing, right? And then after 10 years, we said, okay, I should be able to text, right? Or some very few data, right? And after 10 years, we said, okay, let us have more data, more broadband. And that's where emails and Gmails, these applications, and again, see the application, right? And then 4G things, exploded, right? We have so many applications. Now the network is not about network anymore. Network is about providing service to enabling applications. People know Netflix, people know Google, people know Facebook, but people don't realize that this is only possible because of the internet, right? And now together with 5G, right? So people don't realize that, but that's the fact. I mean, until and unless these networks support what those applications need, there is no Google, right? So, and then in case of 5G, again as a baseline, right? So 4G was good enough, to be honest. And as of today, I believe most of us still have 4G, and I don't think we have complaints. We are able to browse, we are able to stream videos, we are able to download videos, right? So basically, it's meeting all the requirements that we need. Then why did we even need a 5G, right? At that point. So these were the reasons. So it's not about humans, it's more about devices. 5G was more about devices. Devices need milliseconds of latency. Devices need this ultra reliability. For example, you are dealing with some kind of remote surgery application. Now that's where you cannot do away with milliseconds, let's say hundreds of milliseconds of latency. If your video do not get downloaded for a few hundred milliseconds, nobody really cares. Even second, possibly not too much. If it's in minutes, then you will, okay, it's buffering for so long, I don't need it. I will switch to another video or try to refresh the internet, right? But the machines, it's very, very sensitive to that. So these are the three reasons, and I'll briefly look at this. So these were the key use cases or key application, that drove the need of 5G. It's called enhanced mobile broadband. That's just an extension of the broadband that we already have. Okay, so we already browse, we already watch videos, but now we are going beyond that. We are looking into ARs and the VRs, right? The augmented reality or virtual reality, right? Or this cloud gaming and all those things, or let's say high quality videos, like 4K and so on, right? So again, it's just an extension. Even if you don't get it, it's okay. Will survive. All right. But if you look into this URLLC, ultra reliable, low latency communication, now you're talking about autonomous vehicles. You're talking about, this industrial automation, right? Or let's say the surgery. Now, these are the applications 4G cannot support. It is a plain truth. 4G cannot support. Okay. So that's where the 5G is a must. So to me personally, URLLC is the driving or the killer application which required 5G. 4G was not good enough. Okay. And finally, we have massive machine type communication. It's again going back to machines, right? These IoT devices, now you have millions of devices per square kilometer. Humans, you cannot have millions of humans per square kilometer, right? That's not how humans stay together or work together, right? So for humans, it's not needed. The support of millions devices per square kilometer is not needed. But for devices, like let's say you have this 100-story building, right? And there are sensors in each and every floor, hundreds of sensors in each and every floor. You can easily get into millions, in a very small area. Now that's where 4G cannot support. So these were the key reasons. So again, 5G promises to do this, right? Now the question is, why do we need 6G? Or why do we need NextG? So the answer, or let us try to answer. This is not yet well defined. People are still brainstorming. There is no definition of 6G yet. Okay, so people are still looking into it. But this may be the reason why we need 6G. So I'm trying to give some intuition here that on the technological breakthrough readiness, now we're talking about a space network, right? A SpaceX, OneWave, right? That could be the reason why we need 6G, because 5G doesn't have that support, or let's say the standards or the guidelines. It doesn't simply exist, right? So that's because of the technology. Right now, you're looking at terahertz communication. If you guys are familiar with this spectrum bands, so as of today, most of your 4G and 5G, they all operate in sub 6 gigahertz system, sub 6 gigahertz band. Okay, sub 6 gigahertz band cannot support gigabits, maybe up to 1 gigabit, not beyond that, because of the channel bandwidth, the limited availability of channel, and there is no more band left. Most of those bands are licensed. Recently, there was a licensing going on in India, and I was looking at these numbers, because obviously that's what I do. So this Geo and these guys, they bought some of this 3 gigahertz band for several thousands of crores. Just few megahertz of that band. So just see how valuable that particular band is. Why? Because it provides good coverage. That's a good reason. Okay, but now, but still, it doesn't meet the very high data rate you will need for the success of augmented reality and virtual reality. Those kind of applications, they're extremely data rate hungry. Okay, so there now people started looking into millimeter waves. Millimeter waves is around 28 gigahertz, all the way to somewhere around to 300 gigahertz. Okay, they call it 30 to 300, but it actually starts at 28 gigahertz. Now that provided a lot of bandwidth, up to 400 megahertz channels. So that supports a lot of data rate, but people never get satisfied. right? So we said, okay, there are terahertz band beyond after megahertz band, sorry, after millimeter waves. So, and there, like a colleague of mine from Northeastern, Joseph, what's his full name? Joseph, anyway. So this guy recently showed that that terahertz supports terabits of data between a couple of links, data links. He built the hardware because nothing existed in terahertz. Nothing existed until now. You do not really have devices that support terahertz band. You don't really have the standards and others. So he's like his group is one of the first group who actually saw that this thing works. Right. So now it has become a very hot topic in recent years. Right. So again, 5G, we do not have concept of terahertz. Right, then we have this beamforming, right? So until now in 4G and in 4G, a sub 6 gigahertz band, we usually take omnidirectional antennas. You sort of, uh, let's say, project signal in all the directions. Now we are getting into this beamforming that instead of sending signals to all the direction, you send signal to one particular person. So it's basically the intuition is that with the same light or the same power, let's say the bulb and the torch, okay, with the same power, bulb do not go very far. Torch goes very far. And if you do laser, that goes even farther, right? Why? Because it's so narrow, but it goes very, very far. So that's the concept of beamforming. So obviously things have started in 5G, but it's not yet there. We do not see deployment of millimeter wave 5G network yet, because of some limitations. So this is a topic I also work on. And then the application, like I said, right? Applications are the sole reasons why there is so much momentum going on in wireless network, or even I'm not sure about internet. That's not really my field. I'll leave it to Satadal to look into that. But in case of wireless services or let the application are usually the drivers of new capabilities, new technologies, and so on. So here are some applications as you see: holographic, right? The smart grids, right? Remote surgery, right? So these applications are still yet not being supported for their unique requirements. So let us look at a couple of application. So here, for example, right, the smart grid, they might need a low latency of microseconds. 5G do not support microsecond. The minimum you can get with 5G just between the base station or the closest the thing you see on the roads or on top of a building, the base station with some antennas, even that takes about millisecond. Talking to a smartphone, and then now imagine I'm trying to talk somebody in Nepal. Nepal is my home country, by the way, is my country of origin. So I'm talking to somebody in Nepal, so I must go through the internet, right? I'm not even talking about the delay in the internet, right? Just even within 5G, you cannot really support microseconds as of today. But these applications need microseconds, okay, for the control purposes. Similarly, self-designing joint, right? That's computing, the communication, the caching, the control. So there is so much, new innovation is needed to support these enabling or new applications. For example, this one, the capacity, tens of terabytes of data. Now, sub 6 doesn't support millimeter wave also do not support terabits as of today. So now we are looking into terahertz and all. So you see why we need a NextG, right? Because there are this upcoming application that needs to be supported by the network, and network doesn't support yet. So we are doing research or trying to come up with new technologies, right? Why do we need satellite network? Because 5G do not provide coverage to every user, or let's say to this guy, let's say a person in the middle of a sea. 5G will not do that, right? So who is going to provide coverage to that guy? Or a person, somewhere in the middle of a very rural area, right? 5G is not going to be deployed there. It's just too costly, right? So maybe satellite is the solution to that, right? And that's what SpaceX promised, right? If you see the reason SpaceX actually started and US government gave $1 billion or so, right? because they promise to provide 5G coverage or internet connectivity to these guys, who 5G do not currently provide connectivity to. So there is a reason why a technology exists. Okay, so now the question is, I think this makes sense that we possibly need a next G, or we possibly need a new G, which obviously would be 6G, because after 5, 6 comes, right? Unless we skip 6. So these are some of the trends that will get us there. Okay, so for example, more bits, more spectrum, terahertz, right? That's a good example of that trend one, right? Second one, new technologies. So we're talking about metamaterials. And one of the work I do is on reflective intelligent surfaces. Okay, I'm not going to go there. But there are new technologies or new capabilities that did not exist until last few years. It's just being developed. So new capabilities, new research, new addition or new trends of research there, right? Then antennas and RIS, that's what I briefly talked about. New application, right? New services and new media and so on, right? There's so many reasons or so many trends that we see in NextG research. One of the research that I'm very interested in, that can you use 5G signals to locate a user? Now the question is, GPS already do that. Why do you want to do that? Right? So the answer is, GPS do not work indoor, right? Especially in several story building, you will not find good GPS signal, right? GPS do not provide you Z axis. GPS provide you X and Y, right? On a floor, but it doesn't provide you, it cannot, right? Because satellites are up in the air, and what they do is basically triangulation, right? That if I don't know the location of Durgapur, but I know where the Kharagpur is located, or where Kolkata is located, and where Bardhaman is located, then I can do math, right? That, oh, this guy is XY, is 20 kilometers away from here, that guy is somewhere, that guy is somewhere. So it must be somewhere here, somewhere here, somewhere here. So it must be here. That's what triangulation is, right? So that's what satellite does. That's what GPS does, right? So again, no G axis, right? It doesn't work indoor. So now 5G can actually work. Why? Because 5G is very close to buildings, right? You can leverage that. 5G, a small cell, could be inside the buildings, right? So there are reasons why you may use 5G signal for positioning, or Wi-Fi signals. There's a lot of good research on Wi-Fi positioning, right? So that's one of my research area, 5G positioning. There is another good application of sensing, and then communication is the first thing we started with, right? So these are some of the trends. So I hope it makes enough discussion on the application trends. Now let us try to see what exactly a 5G is, or even a cellular network is. So at a very high level, this is what a cellular network looks like. So there is internet, but internet is not a part of cellular network. Okay, cellular network starts at core. Okay, core is basically um, sort of a brain of the network, which takes care of, let's say, subscription or mobility, or those kind of things. So for example, you are subscribed to a particular, let's say, Verizon in US. Here, let's say, what are the companies here? Geo. Okay, so let's say you are subscribed to Geo, right? How are you going to pay Geo, right? So there must be a capability somewhere who keeps a database, or who maintains a database, that you are a subscriber to Geo, and you are subscribed to this particular plan, right? So that's what mobile code does, using something called home subscriber system, SSS, right? Let's say you are traveling from Durgapur to Kolkata, right? So you are here under the coverage of a particular base station, right? But when you travel, obviously that base station is not going to provide coverage, right? So you are going to get into coverage of another base station, from then another base station, and then another base station, right? And you are streaming a video, you are on the call, but it doesn't get dropped when you go from one base station to another base station. Who manages that? The core. Okay, so it's called access mobility and management function, AMF. So basically, core maintains all these different let's say, things about user mobility, or even when you try to access the internet. Right? Let's say you are using your 4G data to access youtube.com, right? But again, like I said, YouTube server is somewhere on the other side of the internet, right? So who is going to manage that? Okay, so web traffic. This must go away from the cellular network to somewhere in the internet and so on. So the mobile core does it. So there is something called packet gateway or serving gateway that manages all that. Okay. Okay, that's not my research area. Okay. My research area is RAN. Okay, RAN stands for radio access network. Radio access network is nothing but your base station. Okay. So, these antennas that you see, antennas, and there is a small thing closer to that antenna, that is your RAN or that is your base station. Okay. So RAN is simply a term or umbrella term which comprises all the base station of a particular, let's say, network provider. Okay. Let's say Geo. Okay, and there could be millions of data, millions of base stations deployed, and let's say in the size of India, right? Because the base stations usually do not go beyond few kilometers. In rural areas, in urban areas, you may want to have a denser deployment. Why? Because there are more people to serve, right? And each base station has a particular bandwidth, so you can only support a particular data rate. And now if you have n number of users, data rate becomes n by b by n, right? And if you want to maintain a certain minimum rate, then you need more base station, right? So that you can serve, or you can you know divide the number of users between two base stations, for example, right? So there could be millions of base stations deployed in the country. Okay. And finally, there's a jargon called UE or user equipment. That's nothing but a wireless device. Okay, whether it's a smartphone or a sensor or anything that connects to the 5G network or 4G network. Okay, or Wi-Fi. Okay. But in Wi-Fi, we don't call it UE. It's a 5G jargon or 5G terminology. In Wi-Fi, we call it client or whatever. And there we call it access point. Here we call it base station. Now within base station, we have other terminology called E node B for 4G base station and G node B for 5G base station. I don't know what they are going to call in 6G. Maybe X node B. I don't know. Okay, but G node B is the latest terminology. Okay, I will let Sadadal handle that. Okay, so I'm going to talk about RAN today. So let us look at the RAN. So the current RAN, the 4G RAN, which we call EU-TRAN. Now, there are a lot of acronyms, a lot of jargon in our field. So you don't need to be scared of that, or you don't need to worry about that. But it's basically RAN. I hope RAN is clear, right? RAN or base station, that's clear, right? Okay. So the current base station deployment that you see, they're usually monolithic, inflexible, black box, proprietary. So basically, what does that mean? That means if you purchase a base station, let's say you purchase a radio, okay, from Ericsson, then you'll have to purchase each and every component of that base station from the same company. Why? Otherwise it won't work. It's like Apple product. Okay, if you purchase a laptop from Apple, you must purchase the charger from Apple and other things. Otherwise it don't work. Let's say something like that. So that doesn't work, right? So there is a monopoly, and that's the reason why these three big companies, Nokia, Ericsson, these guys has like 90% of the market. Okay, we don't want that. Why? Because obviously it becomes expensive, monopoly. US government doesn't like it because none of those companies are US based, right? So what they decided that we must break this base station. We must disaggregate the base station. Okay. So if you disaggregate the base station, then obviously now more players will come in. If I'm good at building antennas, then I don't need to worry about building the other stuff in the base station. I'm good at it. So as long as my antenna work with any other company's rest of the base station, people will buy my antenna, right? So it brings competition in the field or in the market, and it's flexible. And why? As you see, antenna can talk to other part of the base station and so on. It's programmable. Why? Because of the SDN concept. So here also we use this concept of control plane and data plane. So we take everything that is possible to be done at the server than at the real hardware. we take them and put on a server. Okay, so now it becomes programmable. It's literally a software, okay, running on a server and controls different part of the RAN. So I will briefly go into more detail there, but that's the idea. Okay, so this is where the concept of open RAN comes in. Okay, or next generation RAN. Okay, and why RAN is important? So first of all, RAN is extremely important because it accounts for 90% of the cost for any cellular deployment. Okay, just imagine, right? Because phones are owned by the users. Users buy it, not the company. Core is just a software, piece of software, and you just need one or two cores for the entire country or for the entire state. But RAN, you need millions of base stations. You need to. So the business model there, right? If you deploy a base station at a particular land or on the top of a roof, the company has to pay the monthly rent for that. So the OPEX, the operational cost, and the CAPEX, the capital cost, both are very expensive. And then let's say now we are moving from 4G to 5G. Why has not the world been able to move from 4G to 5G or even 3G? In some part of the country, we still have 3G. Why? Because the overhead is so high. We have to remove everything from 3G and then deploy a new hardware for 4G. That is extremely, expensive. Now the virtualization or this softwareization thing, now this will make the life easier, right? Because you simply update the software and it becomes 5G. Right? So once you have that ORAN compatible or this open RAN compatible devices, the next version of the cellular network or next generation of the cellular network will become extremely easy. The OPEX will be extremely low, right? The operational cost. So this is why ORAN is becoming an extremely useful concept, and it's being backed up by almost 350 plus companies around the world. And it's being supported by the U.S. government recently as a part of Science and Chips Act. They allocated about $1.5 billion so that the companies move to this ORAN compatible 5G, 6G, and NextG systems. Japan is already deploying ORAN based systems, right? This is a player in so it's not established player. So we have three big operators in the US: AT&T, T-Mobile, and Verizon. So this is trying to be the fourth operator, okay? And this is deploying ORAN compliant 5G system, okay? So there is a very good reason why we think that the next generation of cellular network will be Open RAN or ORAN based, okay? So here there are basically two core principles. One is openness, and that's where the name comes from, or Open RAN, right? So what is openness? So openness actually comes from these interfaces, a part of, let's say, A, B, and C. Let's say A, B, C together makes the base station. Now you divided the A, B, C into A, B, and C, right? Then this A must talk to B. Or let's say, for example, in this laptop, right? This laptop must be able to talk to the projector, right? So there is an interface here, right? So as long as any laptop in the world, as long as they support this interface, let's say USB 3.0 or whatever, this laptop is usable, right? So that's what's happening in the RAN space. So the A must talk to B, B must talk to C, and that interface we made it open. That interface is openly available. Anybody can use it basically. And the other thing we did is we put the software, like I said, now we are making almost everything that is possible to be softwareized. We softwareize them and we put them on any open server, any COT server. Okay, so that's where the openness is actually coming from, the interface and the server, or this openness of the system. And also the ORAN code is open source. Okay, so that's another thing. And the second piece is intelligence. Now, because it's programmable, now you can program it intelligently. Okay, so that's where the intelligence come in. So that's what it is: open interfaces, open APIs. Okay, so if this makes sense, let us look into this concept called rig, which I'm going to get into more detail in few slides. But these are basically your external APIs that control different aspects of the 5G RAN. Okay. For now, let us stay here, but we'll get into the details. So here I just put some, let's say, motivation or the reason why anybody should do ORAN. As you see, people are doing this, right? Just quite a number of articles. This is from 2021. Recently, I added from 2022. As you can see, like a lot of activity going on, a lot of momentum is going on in this field from across the world, right? Ericsson CEO, for example, or this network I just mentioned, right? Or even India, like Geo, is actually looking into this concept of ORAN and trying to deploy. Why Geo? Why Geo? Why not others? Because others already have deployed network. It's hard for them to upgrade to ORAN, based 5G network. Geo, they don't have the network. They're very new player, so they can make those switches very easily. So there is not a lot of overhead for them. So for example, I mentioned about Rakuten, right? Qualcomm. So there are a lot of different activities going on. And this is the project that we're working on. I just added that. And this is literally the ORAN based project. Like I mentioned, India, right? So there is this, I was attending this, not fully, but I was keeping a track of this particular thing called India Mobile Congress. This is sort of the Indian version of World Mobile Congress, where all the big companies, all the big players come together and showcase their capabilities, their new products and so on. So it's a big event in our field, in wireless field. So there also I saw a lot of excitement about ORAN in IMC or India Mobile Congress. There was this recent proposal which was made public. This is for faculties here. So there is this technology, telecom technology development fund and all that, and they are also pushing to do research in this ORAN or flexible disaggregated 5G networks, which is literally ORAN systems. So now the question is, I made a case that why ORAN is so important, right? And try to give some core principles of ORAN. But what exactly is ORAN, right? So let us try to look into that. So at a very high level, so the blocks that you see, this is RAN, okay? So in old days, these were all together within a single black box. Now what we did, we divided that into A, B, and C. Now, even within C, we have two different parts. Let's not worry about it. So this A is called radio unit. O stands for open. So open radio unit. So what is that? That is simply the antenna and the very lower layer physical computation. For example, digital to analog or analog to digital conversion, right? Because in air, you don't really do digital, you do analog signals, right? And then when it comes to the system, you convert that into 010101, right? So that's what's happening there. Okay, over here, radio unit. So these are the some of the operations you can't take it to the software. Okay, because they are too hardware based, and second, they must be very fast. So that's another good reason why they are not. But other than radio unit, everything else could be on the software. Okay. So for example, the Mac layer, if you're familiar with the networking concept, here we do scheduling and other things, right? So that could be, now again, scheduling has to be fast in milliseconds, but it doesn't need to be very fast in microsecond or nanosecond, right? So in that case, we can put them on a server close to the base station, right? Like a ACE server, very close to the base system. So that is called distributed unit. Okay, let's not worry about the other blocks. And the last one is called control unit. The control unit is more about controlling the functionalities within the RAM. Okay, now this one is taking care of the data. So that's called user plane, UP, user plane. Okay, and this one is taking care of the signals, the controlling signals, and that's your CP, control planes. Okay, and as you see, this talks to AMF. I briefly talked about AMF. Right, that's your core functionality, and then UPF stands for user plane function, and that's also a core functionality. But the only takeaway message here is that it's a disaggregated RAM.
and there are three components. That's it. As long as you understood that, the job is done. Okay. And between this block and this block, there is an open interface. Between this block and this block, there is an open interface. Between this block and this block, there is an open interface. Okay, but they are 3GPP defined interface. Okay, so these are the interface that already is being taken care by 3GPP. If you don't know 3GPP, it's basically an international body that sets the rule for any generation. Okay, that what are the new technology it must support. How should it work? For example, the satellite network, right? How does the satellite network work? Right, that will be defined by 3GPP. So as of today, I'll just give you an example. As of today, we are in release 18, and release 18 in 3GPP for space communication do not support space to space communication link. Okay, so a satellite can only relay the packet from a base station to another base station or another core. That's it. It doesn't mean you can't do research. It's just that 3GPP has not done it yet. So the companies, if they build products, if 3GPP compliant, they cannot support satellite to satellites. And that's one reason why SpaceX is not a 5G concept or a 3GPP compliant cellular network. Okay, but it is a wireless network. So the ORAN brings this. Okay, it brings new interfaces. For example, E2 that goes from, okay, we talked about RIC, right? The RAN intelligent controller. And I said it controls different aspect of RAN. For example, it controls how MAC should work, okay? Or it controls how radio link control should work, right? It controls many different aspects of RAN, right? But based on the time requirement, it is of two types. The near real-time RIC or near real-time RIC, which is from 10 millisecond to 1 second. Okay, and anything beyond 1 second is non-real-time RIC. Make sense? So now think of an application, right? So scheduling, where will you put it? In near real-time RIC. Why? Because the scheduling has to happen in milliseconds, right? But let's say you change a particular rule, right? Let's say there is some service message or control message that change every hour or every day for whatever reason, right? So in that case, you can do those network configuration in non-real-time RIC. Okay, let's say you want to have a machine learning based scheduler or machine learning based some functionality, right? So in that case, where do you train your model? In non-real-time RIC. Why? Because you don't really train a model in milliseconds, right? But you want to use the model to make decisions. So the trained model or the inference model, where will you put it? In the near real-time RIC, right? So you see how the name comes in. Now there is near real-time RIC, there is non-real-time RIC. Obviously, there should be a real-time RIC, right? So we are building that. Okay, it doesn't exist in ORAN specification, but we want to change ORAN specification. Okay, so this is a bit more detailed. So here I show you the interfaces. For example, the RU and the DU open front hall interface. You already, okay, let's not worry about this. So what I'm showing is that this is your RAN piece, the RU, DU, and CU. And the only thing I'm showing extra is the interfaces and the concept that one RU can support multiple DU and one DU can support multiple RU. Okay. So for example, NIT Durgapur, I may have 10 RU. Why? Because the coverage is limited, right? So I will have 10 RU, but I can control all the 10 RUs from one DU. Okay. Then for the entire NIT Durgapur and Durgapur, let's say Benachiti and City Center and NIT Durgapur, I can have 3 DUs and I can put one CU at the Durgapur level, okay, or even at the state level. So just trying to give you an idea that this thing could be hierarchical and scalable. Okay, so this is your RAN piece. That's your near real-time RIC, right? And we briefly talked about that, right? So for example, the ML model could stay here, right? There could be some kind of load balancing. So basically more time critical application. And we call it X app. X basically means extended applications. Okay. Okay, makes sense. So the jargon, but X app. Okay. Now there is something called SMO, Service Management Orchestration and Automation. But within that, if you see there's a non-real-time RIC, you see let's say the policy or the configuration and so on. I do not see the training model there, but you can have the training model over there, right? And there, if you have an application, then we call it R app. Okay, R stands for remote application. Okay, and you see how that name, how there is such name, right? Remote because it's not really critical; it's more than a second. Extended application because it is an extension of RAN, but it is still time critical. So just a good idea. This is a nice analogy. I can give analogy from Sataro's work, right? So if you look at the switch, right? So the old days switch, we had the control, let's say the routing algorithm, and the actual data forwarding table on the same switch, right? But now what we did, we disaggregated that. We put the logic in the control plane, right? And then we put the hardware is still there in the switch. Now who manages that? So there must be a controller, right? So in a way, that's your switch operating system, which is managing, whatever functionality you want to implement, whether it's routing or whatever it is, or let's say firewall or whatever, right? And you are making changes to the real hardware through the operating system. So the application do not need to worry about how the hardware is being handled. So that is something similar going on in the cellular RAN space. Okay, so now you worry about your scheduling or worry about different RAN application. Okay, whether it's scheduling, slicing, load balancing, and so on, but you don't need to implement on the real hardware. Okay, so I call it RAN OS, for example. Okay, so just imagine, right? So the way operating system has revolutionized the computers or the controllers has revolutionized the switches or the internet, today's internet, I am expecting that this ORAN or the RIC will revolutionize the 5G or the cellular network in general. Okay, so right now we are building the operating system for cellular network. Okay, so that's where we are at. So just imagine after 50 years what will happen. Like again, go back to the computer field, right? We used to have mainframes or the typewriters, right, where we will directly interact with the real hardware, and then the guy who came up with the concept of operating system, Bill Gates and the Apple founder, they became millionaires and trillionaires. Why? Because they built the first operating system and see the world, how the world has changed, right? How the computers have changed, right? And that's you must give credit to the operating system, and or let's say this is smartphones, right? It's Nokia. Does anybody use Nokia? I mean, even Nokia used to have operating system, to be honest, right? The symbiosis. So just see the future here. Okay, so this is the background. I hope now we understand the beyond 5G application, beyond 5G trends, and beyond 5G architecture. So this is what I was talking about. This ORAN is your architecture. Okay. So we completed that. Now I'm going to get into the some of the research that we're doing in this field. How much time do we have? Till one? Okay, 15 minutes. Okay. So ongoing research. Yeah. So there are quite a, let's say, small sub projects that's going on in the group. Obviously, they're all in the NextG. They all belong to the NextG research. So the first one is called OpenAI Cellular, which is sort of a foundational project for all the other projects that I'm doing. Okay, so it's a really important project for our group. And the good thing is that we have made this, we have made everything that is developed under this project fully open source. So if you want to get into this field, you can use our softwares. There are documentations, codes, libraries, software, everything is publicly available. If you Google www.oaic or openaicellular.org, you'll find everything related to that. So I'm looking at this concept of network slicing. If we have time, we'll talk about that. But the idea is very simple. The idea is that that the 5G, for example, or cellular network in general, right? We're trying to support EMBB, which is several gigabits of data. We're trying to support URLLC, which is not about data, right? Let's say remote surgery, for example. They are not sending gigabits of data, right? But they need ultra low and ultra reliable latency. So see, these are conflicting quality of service requirements, right? These are conflicting requirements. or let's say MMTC, for example, right? There's millions of sensors, but they are not even sending you a lot of data. They don't even need low latency, but what they need energy efficiency, right? The millions of data, they need those support for multiple devices, right? So the requirement that is expected of 5G is different for different applications, right? And the single 5G cannot support all those applications at the same time. So that's why we came up with this concept of slicing the network. Okay. So slice, when I say slice, do not really slice physically, but slice logically the network so that a particular slice can meet the expected requirements for a particular application. Okay. So if I'm supposed to support URLLC application, let's say vehicular autonomous vehicle, then they will all subscribe to this URLLC slice so that that slice has been designed or configured to support those requirements, not bandwidth, not data rate. It is supposed to support reliability and latency. If I'm trying to do augmented reality, then you subscribe to the EMBB slice, right? Which provides more bandwidth, but it doesn't support reliability or low latency, right? So you see why we need slice. So that's the research we're doing, that okay, how are you going to create those slides, right? What are the logics, right? What are the implementations, right? So that's one research. The other research is on spectrum sharing. This is fundamental to any wireless research because wireless research operates on some frequency band or some spectrum band, right? So, and the spectrum band are limited resource. We have billions of devices now and possibly trillions of devices once the Internet of Things and Internet of Everything becomes widespread. So now where are we going to get a spectrum from? Like if you license a spectrum to a particular company, right, then those are licensed, nobody can use it, right? So if they can't use it, where are the new devices going to operate on, right? So that's why there is a need of spectrum sharing. We have to share the spectrum, but the question is, how are you going to share the spectrum, right? So if there are licensed users, you cannot interfere them, right? Because they paid billions of dollars to purchase or license that particular spectrum. So we are doing a number of research on, for example, 3 gigahertz spectrum sharing. So 3 gigahertz in US belongs to the government, federal government. So and but they are doing it for the radar purposes, to detect any alien ships or alien planes, right? But as you see, the number of use cases is very limited. They will be usually deployed at the edge of the US, right? At the boundary of the US, right? So within US, you can use that band. Right. So how do you share that spectrum? So there are a lot of ongoing research. Then there are other bands, for example, 12 gigahertz band, right? That is allocated for direct TV, the satellite, the TV that you see at homes, right? Again, that is just one-way communication. The TV is simply receiving signal from the satellite, right? So we are making a case that actually terrestrial 5G network can coexist in that particular band. Right. So there are a lot of good research going on in spectrum sharing. Like I said, we are doing a lot of good work on beamforming, which I gave you an example of touch and laser. So that's the kind of work we're doing. We're looking into 5G positioning. Like I said, how do you position a user, especially in indoor setting, using 5G signals? Because 5G do support positioning architecture. And then they do support a couple of new signals. It's called sounding reference signal and positioning reference signal. They are dedicated or designed for positioning, not for communication. Okay. They allow you to collect different measurements, for example, angle of arrival or angle of departure, right? Or TDO, the time difference of arrival, right? Or RSSI, the received signal strength, right? So there are a lot of good measurements that 5G signals support that you can capture and locate the user. So this is another research that we're doing. We're also looking at some enabling application. I talked about smart grids. So we are looking into that application in collaboration with Power and Energy Center at Virginia Tech, right? That then they have this nice smart grid test bed, and they, as of today, they use this wired links between different devices. But now that's not scalable, right? Because in smart grids now we are seeing the rise of using a lot of sensors, to collect reactive voltage or current and so on, right? Because now we have solar panels, we have all these different things that change with time, right? So the generation changes, so consumption will change. So how are you going to maintain the stability of the grid, right? So that's where we are looking that, okay, can 5G be the solution to solve that problem? We are looking at satellite communications. We recently received a grant to study this with University of Surrey and Space at Virginia Tech. So here we are looking how the satellite communication will be a reality, and what are the different challenges. For example, this SpaceX is deploying hundred thousands of satellites. Then Amazon is deploying a lot of them, and then this Kuiper, and there are so many different. Even India, in collaboration with UK, is deploying a lot of satellites. How are they going to coexist, right? So there are a number of challenges that has to be addressed. So we are looking into that. So as you see, there are a number of different research that we are looking into. And the last one, I mean, there are more, but here the last one is application oriented scheduler. So I talked about scheduling, right? And as of today, if you look, all these scheduling algorithms, they are designed to improve a particular network performance, like a throughput, latency, energy efficiency, and so on, right? And I'm saying you, right, that 5G and 6G are supposed to support application, okay? So for example, you are watching a video, right? I don't care how much latency you got or how much throughput you got. As long as I'm able to play the video without any interruption, without any waiting, without any buffering, that's what I care about, right? So it's about quality of experience. It's not about a network quality of performance or quality of service, right? Or let's say you are looking at some kind of monitoring application, right? As long as I get the most recent data, right? Then that is good enough for me. I don't need all the data, right? If I'm taking, let's say, the heat measurements, okay, or the, let's say, moisture measurements for a particular soil, let's say for the agriculture IoT setting, then I don't care if all the packets are being delivered or not. What I need is the latest information, right? So there, it's about information freshness, not about information latency. So there is a reason why we need to move from network centric communication to application centric communication or user centric communication. And I think that will be the principle of 6G. The 6G will move away from network and focus on user. User will be in the center, or application will be in the center of the 6G design or 6G development. So I have 7 minutes. So let us look at least one example. So okay, so the OAIC, right? I talk about this at almost all the places. Like I said, this is the founding or the foundational project for us. So what it does is basically provides an open platform or open source platform, which includes software, libraries, tool set, documentation for prototyping and testing. Okay, the AI based RAN controllers. Okay, makes sense? So we want, because AI will be native to 6G, and that will be one distinction between 5G and 6G. So 5G doesn't really deploy AI yet, but in 6G it will be native to the network, right? So now the question is, the AI you cannot explain, you cannot interpret, you do not know how it works, right? Because it's all about equations. So you're just doing some linear equations when you talk about neural networks, for example, right? You do not know what the bias values mean. You do not know the number of nodes mean, the number of hidden layers mean. If you're familiar with the neural networks, you know that it works. You know that it gives you 100% accuracy or 99% accuracy, but you don't know why, right? How do you trust? How do you trust your billion-dollar company on something that you do not know what's going on, right? So the question is, you must at least test those models across different settings, right? Like do a rigorous testing so that at least you understand that, okay, this thing, even though I don't know why it works, I have tried out all the combination. For example, if you train a model in Durgapur and try to deploy in Kolkata, possibly it will not work, right? So, you have to test in Durgapur and Kolkata and see if it works, and possibly, some other scenarios, right? So to get some confidence, right? Because you are risking your business there, right? So if your AI doesn't really work, right? Then the user service will become bad. A user will get frustrated, right? So there are reasons why you should obviously, we see the promise that okay, AI is going to help us, but we do not yet understand how AI works. Okay, and there is some ongoing research, unexplainable AI, that they're trying to understand. But until we are there yet, we must test. At least we should test. So that's what we do. So it has two components. One is the controller that we want to build AI controllers. The second piece is we want to test them. Okay. So now what is OAICC, or this OpenAI cellular controllers? So this is basically a marriage between three things. The first one is the ORAN architecture, and you know ORAN architecture now, right? The RIC, the near real-time RIC, and the non-real-time RIC. Okay, so this is near real-time RIC, this is a non-real-time RIC. Okay, and then it must work with 5G. So for our platform, we use open cellular softwares. Okay, so we use SRS RAN. That's one of the two very popular or prominent cellular software that is available. One is called Open Air Interface, and the other one is SRS RAN. So we use that software for the base station, which is RU, DU, and CU, and we use Open 5GS. That's open source core software that's available. And then for the radio front end, we use software defined radios. This X310s or anything. These are basically USRPs. It also works with software. It's called 0MQ. That's the software version of 5G networks. And then it also works with CORDS UV. So this is, as you see, it's a marriage between this ORAN architecture, which is this piece, the 5G N1 protocol, which is over here, and the software radios. Okay. So that's what OAICC is. Let's skip this. This is a small testbed that we have developed in the lab. But if we need a bigger testbed, we also have access to the CCI NextG testbed, which is, I think, the biggest or the largest university-based testbed in the country, in US at least. So, and these are some of the XApp that we have developed. Okay, so these are some of the existing XApp which already exist by other people in the field, in the community. They are mostly industry-based XApp. And then these are the new XApp that we have developed. So Age of Information Scheduler, which is sort of an example of application-based scheduler. So that is something we developed. Then we have developed some machine learning-based resources scheduler. We have looked into this RAN slicing scheduler, the spectrum sharing or the spectrum sensing spectrum sharing XApp. So these are some of the XApp we have built. Positioning, beamforming, we're still in the process. And then this is what I was saying, that beyond XApp, the real-time RIC, this is something we are also looking at, that can we have less than 10 millisecond latency in the ORAN architecture. Like I said, the core documentation, even the YouTube channel, it's all open source if you want to try out our software. And then we have the testing piece. We have this nice testing framework. I'll not go into the details in the interest of time, but I would like to say that we just released our first version of OAICT last week, soon after the New Year. So it's our New Year gift to the wireless community. Okay, and that's a nice, not nice, but very basic GUI that shows you some of the testing results that you may have run on 5G networks. So I will, I think, skip all these slides. I will skip all this slide for now. Okay. Oh, by the way, I'm hiring PhD students to work on some of our projects. So if you guys are interested, do reach out to me. And these are some of the students I must acknowledge because I'm here because of their work. I also advise few students at Virginia Tech, so I have mentioned them as well. Thank you.